let's put some pictures here. If I have this graph, I get these 3 points. That's one of them. Or if I have this graph, starts here, and it goes like this. You can put X and Y axes anywhere you want to. We don't care where they are. You know, you can put them anywhere you want to. We have a closed interval. This function is only defined from this X value to that X value. Finding the extrema is finding the minimum and the maximum value. Now, if you look at the picture here, when you look at this point here, in this neighborhood, what is this point? Is that the smallest value or the largest value?
Smallest.
That point in this neighborhood. I circled the neighborhood.
It's the largest.
That's the larger value. That's larger than any value in that neighborhood. When you look at this point here, in this neighborhood, surrounding it, what is that point there? Is that the largest or the smallest value?
Smallest.
When you look in this one,
Largest.
that's the largest value.
Oh, so when you say neighborhood, you mean like,
In that little circle, around that, yep.
oh,
So this is actually, we call that relative max. In this neighborhood, that is the largest value, minimum value, or in this case, maximum. This one, relative min. I was looking at the book to see, because there's some people, instead of relative, they use the word local. So instead of relative, you might see it if you decide to Google it sometimes or look at a video. They say local min, local max. You'll hear me use both of these terms. In this neighborhood, that's also what? A maximum value, relative or local max. I'll come back and revisit these. What about this point? That's a relative max. What about this point here? Relative min. What about this point here? Relative max. And this point here, relative min.
So can you pretty much just say it's or separate the neighborhood by the quadrant? Or?
Not by the quadrant. It has nothing with the quadrant. I could have made them all in the same quadrant. The picture.
The slope of the line.
It's actually not the slope, the y value. This is the largest y value. That's the smallest y value. The smallest y value, the largest y value in this area. So not the slope, not the quadrant. It just happens to be in this case. I could have moved my axes right there, put them all in the same quadrant. Now, out of this entire graph, where is the largest y value? That's this one. So over the entire graph, that's the largest value. We call that absolute max. That's an absolute max. And where is the smallest y value? Down here. That point is what? Absolute min. So absolute, that means over the entire graph. Relative, just in the neighborhood. Looking at these, which one is the absolute min, which one's the absolute max? If I drew that, that looks like an absolute min, doesn't it? And where's my absolute max? Does it look like that one? So if they ask you where is the absolute max, it's right here, whatever that x value. What is the absolute max is the y value, whatever that number is. Instead of absolute, sometimes they go global, not local. Then they decide to use global. Global means over the entire graph.
So instead of absolute, they use global?
Yep. It's not often you see in the math book global, really, but our book mentioned that. I've seen a lot of books use local instead of relative, a lot of them. But global, it's not often you see it in the math book for absolute. But don't be surprised to see it. Our book talks about absolute or global. The question is, how do we find where these values are? Well, let's look at these points. We have 3 points here. This is what? That's the end point, right? And that's also the end point. So if it's going to be where the end points are, but that's not an end point. What is that point?
Limbo.
This point. Let me ask a question. What's the derivative there? Why 0? Slope of the tangent line, right? If you draw a tangent line, what's the tangent line looks like? Right? Horizontal. So your absolute min, your local min, all of them either going to be where the endpoints are or where the derivative is 0. Let's look at these 4 points. These two are what? The endpoint. What's the derivative here? 0. What's the derivative here? 0. So that's one of the applications, where we find these points. The absolute min, the relative min, absolute max, relative max, either going to be located at the end point or where the derivative is 0. So I don't have to graph them anymore. Let's take an example without graphing it and see if we can find where the absolute min, the relative min, max, f of x equals x squared minus 4x plus 5, and we want it from the interval minus 1 to 3. What's the derivative of that? So your min and max going to be either at the end point at minus 1 or at 3. Or, where's the other option? So the min max going to be where? Either at the end points or where the derivative is equal to 0. So let's take the derivative and set it equal to 0. 2x minus 4, set it equal to 0. 2x equals 4, x equals 2. So there's 3 points to test. I'm going to be testing the negative 1, I'm going to be testing the 3, and I'm going to be testing the 2. These are the end points. This is where the derivative is 0. What is the value of the function, not the derivative at minus 1? That'll be a 1 here, plus 4, plus 5, which is what? 10? What's the derivative? The function at 2. 4 minus 8 plus 5. Is that a 1? And what is the derivative at 3? Nine minus 12 plus 5. Negative 2? Can't be.
No,
Plus
it's
2.
Positive two.
Plus 2, right? So where is the largest value?
At -1.
Right there, right? So your absolute max is going to be where? At negative 2, comma what? 10? And what's your absolute min? This one, right? That's the smallest y value. At 2 comma 1. If I graph this on my calculator, where's my calculator? If I graph that function, let's see if it agrees with us. I'm going to change the window here, minus 10 to 10. So I get to see, because I see it going to 10. Now I'll go minus 10 to 10. Let me clear that. And let's graph that. X squared minus 4x plus 5. Graph it. X goes from minus 1 to 3. Let me zoom in on that window. X min minus 1 to 3. That's what you're looking at. Can you see the picture? That's your maximum value, and it's minus 1 up here. And your minimum value is somewhere here. Then it starts to go up. So that's your maximum value, that's your minimum value. Now this point, we really can't tell just from these points if that's a min or a max till you graph it. This point here. You don't know. Just because the number is 2 there. Well, the number is 1 here. Go, well, it's higher than that, so it could be. But you don't know what the graph looks like, you know. The graph might be like you might have a picture that looks like this. Then here it could be going like this, right? Or it could go like this, crazy, and it comes down like this. If it did that, then that's really what? That's a minimum value. But if it goes like this, then that point is what? A maximum value. So we're not sure if the graph has something like this, a crazy design. Now in calculus, that's a no-no. V shape is not something we like to see. Because that means what? There is no derivative there. At this point, there is no derivative. The derivative is the slope of the tangent line. The slope is positive from this end, negative from that end. There is no derivative at the V. That's why in calculus, you rarely see a V shape there, except if it's absolute value. You're not going to see it. Let me practice a couple more questions with these. So we've managed to get the absolute min, absolute max just by testing the endpoint and where the derivative is 0. This is the function. That's a different function, actually. X cubed minus 3x squared. Let's look at that from where to where. We're going to look at it. There's only one example here. Come on. I'm sure there's more than one example. basically. Let's take this one, f of x equals 3x to the fourth minus 4x cubed. And the interval from minus 1 to 2. So the endpoints are, we need the derivative before I get to that. What's the derivative of that? 3 times 4, 12x to the third minus 12x to what? Squared. Let's set it equal to 0. Can we factor 12x out, or 12x squared? What's left? X minus 1 is equal to 0. What do you know? We have two values. That will make that 0. X equals to 0, and x equals what?
1.
We call these critical values. CV, critical values. So we have two critical numbers or critical values. So if I look at my left endpoint, I'll put the numbers in small to large. That's the minus 1. We'll see if that's a min or max. The other point we're going to look at probably the 0. That's the critical value, critical number. We'll put the 0 here. The other critical number we're going to test, we'll use which one, the other critical number? The 1. And the last value we're going to be testing is what? The right endpoint. So if you're going to have a min or a max, it's going to be one of these values. And how do we know which one is min, which one is max? We plug them into the problem. F of x. Not the derivative, into the function. If you go back to that function, when x is minus 1, that's what? 3 plus, I think that's a plus 4. 3 plus 4, that's what? 7. What's f of 0 here? Is that 0? What's f of 1? Is that a negative 1? And what is f of 2? 16 times 3 is 48. 48 minus what? 32? Is that 12? Which one's the largest y value?
12.
The 12, that's your maximum value. Which one is the smallest value? Negative 1, that's your minimum. So the minimum value, 1 and minus 1, that's where it's going to be. It's going to happen at 1, it's going to be the minus 1. And the maximum value is going to happen at 2, and the value of that will be 12. I can actually, with these numbers, predict what the graph looks like. And, you know, how do we know what the graph looks like? We have the endpoint. Watch this. This is the minus 1, the 0, the 1, the 2. At minus 1, the value is 7. 1, 2, 3, 4, 5, 6, 7. Right there. At 2, the value is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At 0, the value is 0. At 1, the value is minus 1. So the graph looks like this is where the derivative is 0. For 2 is 12, right? Or 16? That's 16 dots there. That's 12, but I'm not gonna. So the graph actually, it says that's the maximum value here. Down here, the derivative could be 0. We call these points where the derivative is 0 actually, right there, the critical numbers. They have a name also called possible, not always, possible min-max. So if you're going to have a min or a max, it's going to happen here. In this case, that's not going to be the case. It's going to be here, but it's not here. In this case, the graph probably will look like this. Might look like this and goes back up there like that. We won't know really if that's what the graph looks like till I get the second derivative. Once I get the second derivative, I can pinpoint the graph without looking at graphing calculators. It will tell me every single spot in that graph, what's going on. So right now I'm guessing it's going to come down this way, it's going to change its mind, flip that way, and maybe change its mind again. Just a guess there. Or it could just continue to decrease, going through that point, then go back up there. I doubt it that's what's going to do. I have a feeling it's going to actually do some crazy stuff right here. But with the first derivative, it doesn't tell us that. The second derivative will tell us what's going on.
Why is that second derivative?
Now you got to wait on that. That's till Thursday.
The second derivative is just different, another different line.
The derivative of the first derivative. Now, so the extrema or the min-max point is where the derivative is 0 or endpoints. Well, not really true. In the examples I gave you, yes. What about if I give you a problem like this one? F of x equals 2x minus 3x to the 2/3 minus 1 to 3. Let's find the extrema. The extrema. That means I need to find the derivative. What's the derivative of this? 2 minus 3 times 2/3. What's that? 2? X to the power of what? Negative 1/3. Clean it. When you have a fraction, you got to deal with two things now. Not just where the derivative is 0. The critical values or critical numbers. In the previous two examples we did, we took the derivative and we set it equal to 0. That doesn't change. That's still true. But also you got to find out where the derivative is undefined, like in this example. Before the previous two examples, we didn't have to discuss undefined because there were no fractions. Now you get a fraction. So let's find what the critical numbers are, or critical values. Take the derivative, set it equal to 0. Two equals 2 over the cube root of x. That's 2 over 1 if you cross multiply. What's x will have to be? 1. The cube root of what number is 1? There's only one number, the cube root is 1. That's the 1. So where's the derivative undefined? What is it? That's 0 because you have a fraction. When you have a fraction, what value will make the bottom of that fraction go to 0? X equals to 0. So we have two critical values. This is one of them, x equals to 1, and x equals to 0. So now when I tested to see where the min or the max is, I'll begin with the -1. That's the left end, -1, which is what? The left end point. The next one is 0. That's where the derivative, well, undefined, critical value. I put the label on the top. Critical number. That's where f prime is equal to undefined. Can't be equal, so it's it does not exist. D and E. Put some space there. That's the -1, the end point. That's the 0. The other critical number, that's where f prime is equal to 0. And that's the 1. And where's the other end point? The right end point. That's the 3, right? And now let's go to the function and see what is the value at each one of them. What was the function? The function was f of x equals 2x minus 3x to the 2/3. So when x is -1, also that means, by the way, 2x minus 3 times the cube root of x squared. So when x is -1, what do we have? Two times the -1, -2, minus 3 times the cube root of -1 squared, which is 1. What's the cube root of 1? 1, that's a -5. When x is 0, it's 2 times 0, which is 0, minus 3 times the cube root of 0. Is that a 0? When x is 1, 2 minus 3 times the cube root of 1. Is that a -1? And the last one, what's the value of the function at 3? 6 minus 3 times the cube root of 3 squared, which is 9. Let's see what that number is. 9 to the power of 1/3 in parentheses. I'll turn it on first. 9 to the power of 1/3. That's what cube root is. This is 2.08 times 3 plus the 6. This is actually a -0.24. So where is my minimum value? And where's my maximum value? And if you happen to graph that function, this is what the graph looks like. It looks like this. Then it's a V shape, and it goes like this. It doesn't touch it after that. It looks like this. That's your maximum value. There is no derivative, does not exist. There's a V shape here. So this is the minus 1, minus 5. This is the 1, minus 1. This is the 3 and negative 0.24. So that's your maximum value at 0, 0. And that's your minimum value at minus 1, minus 5. So when you're looking for the extrema, you need to find where the derivative is 0, where the derivative is undefined, and the endpoints. Then we'll do the next section, and we'll stop with that.